So I want to describe another simple model, which is called the random energy model. So we can think again at a system of spins, the magnetic system, where this random variable takes value 1 plus or minus 1. But then instead of looking at the easy model, which is a very regular system, where all the spins are the same, there is translation invariance, and we want to study models which are more complicated, which are disordered systems, so where essentially each spin interacts in a different way with all the other spins, okay? And so as a result of this, if the interactions themselves are random, then the energy itself is a random variable. So for example, you can think at an easy model where the interaction between spin I and j is not fixed, equal to j, but it's just drawn at random for every pair from a distribution. Okay, so this is called the spin glass. It's a very complicated system. So we want to study a simpler system, and we want to study what is called the random energy model. And in particular, random energy model is a model where the energy of a configuration X is itself a random variable, and it's drawn from a distribution of energies, which is Gaussian, okay, which is just a Gaussian square root 2 pi n e to the minus e squared over 2n. Okay, so and this for each configuration, I assign an energy by drawing at random from this distribution, and so each energy level is independent and identically distributed. Draw from this probability distribution. So now, why do I choose this variance to be equal to n? Well, because if I want, my probability, the probability should be, or the log of the probability should be the entropy, and or minus the entropy, and I want the entropy to be extensive, to be proportional to n, and I also want the energy to be proportional to n. So if the energy is proportional to n, then in order to get that the log of the probability is proportional to n, I have to divide by n here. Okay. So this choice is to get, in order to get, say, a thermodynamic limit which is well defined. Okay, so then so this is the definition of the random energy model, and well, one can think, well, let's compute the partition function. And now the partition function is a sum of many random terms. And you can think, well, okay, let's, so the number of configurations is 2 to the n. Okay, so the number of possible values of this x is, each spin takes 2 values, so all of them take 2 to the n values. So this is a sum over many terms. So I can think that this is well approximated by 2 to the n, which is the number of terms that I'm summing, times the expected value of e to the minus beta a, where the expected value is taken with respect to this distribution. Okay, and so what is this? Well, if you compute this expected value, then this is just e to the beta squared over 2 times n. Very good. So well, my free energy, which is say minus 1 over beta times the limit when n goes to infinity, or say let's just take extensive free energy, which is minus 1 over beta times the log of z. This is minus 1 over beta times the log n times log 2 minus plus beta squared over 2 times n. Okay, so now this, well, if you look at this, is minus beta over 2 times n minus 1 over beta times n log 2. Okay, so this is the free energy. Now let us compute what is the energy. So what is the internal energy? Now the internal energy is always computed easily by taking minus a derivative with respect to beta of the log of z of beta. And so you see that if you take the log of z of beta, then this is beta squared over 2 times n plus a constant, and so the derivative, so the energy is just minus beta times n. Okay, it's very simple. And then I can also compute, say, the entropy. So the entropy is beta times U minus F. Okay, so this is beta squared is minus beta squared times n minus plus beta squared over 2 times n plus n log 2. Okay, very good. So if I simplify this, well, I just get that this is just equal to n log 2 minus beta squared over 2 times n. Okay. Very good. So this is the solution. Now, if you look at this solution, what you find is that so if you plot the entropy, so the entropy when as a function of temperature, 1 over beta. So when beta, let's plot it as a function of beta. So when beta is equal to 0, which means infinite temperature, then the entropy is n log 2. Okay? And then the entropy decreases just like a parabola. Okay? The energy, on the other hand, is just starts. Let me do it with a different color. So this is the entropy. The energy starts at 0 when beta is equal to 0, and then decreases just linear. Okay. Now, the problem with this solution is that you get negative entropy. So what is going on? Well, this is a system with a discrete number of states, so you cannot possibly have a negative entropy. So because it's so the entropy is the entropy of a discrete variable, so it has to be positive. So it cannot be negative. So what is going on? What is the problem? Well, the problem is that in doing this calculation, we have made this assumption that we can compute the partition function by assuming the law of large numbers. Okay? So, and this means that so when you compute this sum is really dominated by an exponentially large number of terms. Okay? However, turns out that this the terms that we are summing are exponentially large or exponentially small in n. Okay, so this is a situation where the law of large numbers may fail to hold because we are summing exponentially large objects, or variables that have a very broad distribution. And indeed, so there is one way of making sure that what we are doing has problems, which is to say, well, let's compute the ground, how big is the ground state energy. So the energy of the ground state is essentially the minimum over all states of the energies. And well, this is a problem because the energies are all IID random variables, so this is a problem of extremes. So let us compute how big, how small an energy can I have in this system. Okay, so essentially you see that these energies here are square root n times a Gaussian variable with, so I can write this as minus the square root n times the minimum, times the maximum of n random variables zi, or say, let's call it yi, okay, where these yi are essentially Gaussian with mean 0 and variance 1. Okay, so we have done this calculation previously. What we have seen, and here this n is equal to 2 to the n, is the number of configuration of the system. Okay, so we have done this calculation. What we have seen is that to leading order, we can say that this will be equal to minus square root n, and the maximum will be of the order of this AN, okay, and plus there will be smaller terms. But this AN for the Gaussian variable was essentially square root of 2 times log of n, okay? That because the number of variables which I'm taking the maximum is 2 to the n, then this is is a square root of 2 small n times log 2. So this is equal to minus square root n times square root n is just n times square root 2 log 2. Okay? So essentially this tells you that from an energy which is equal minus n times square root of 2 log 2. So here you get the minimal energy, so there is no energy below, there is no energy level below this, this point, okay? So it tells you that actually the right plot of your energy should be that your energy is equal to so let me take this energy a little bit smaller. Okay, so so your if this energy is given by this, then there should be so all of this energy should not be there, and the energy should just be given by this line. Then above this point it should be just flat. Okay. Now, if you check what is the temperature to which this corresponds, it is the same temperature where the entropy becomes negative, because the entropy becomes is equal to 0 when this is equal to 0. So when beta is exactly equal to 2 log 2. Okay. So there is a critical point, and so if the temperature is larger than this critical point, then you are in this region. So this is high temperature. And then the entropy is really exponential. I mean, the entropy is extensive, so which means that this sum is dominated by an exponentially large number of terms, so that the law of large numbers can be assumed to hold here. And then this curve is essentially okay. But in this region, when beta is larger than beta critical, this sum is dominated by just one term, which is the ground state energy. So essentially the entropy is 0, so the true entropy here should be equal to 0. And likewise the energy should just be equal to minus equal to the ground state energy. Indeed, check that, so the energy becomes equal to the ground state energy exactly at beta critical. Okay, so this again is an example of a phase transition. It's called a freezing phase transition, because your system that can explore many states at high temperature, at low temperature, essentially it explores very few states which with an energy close to the ground state energy. Actually, things are much more complex than this, but say at least the thermodynamics of this system is described by this phase transition. Again, notice that this is a phase transition, this is a second order phase transition because the entropy, which is first order of the first derivative of the free energy, is continuous, so there is no latent heat. So, so this is a second order phase transition, but so this is a paradigmatic model for disordered systems.